finally, our last instruction. Branches conditionally transfer control to a specific target instruction, but will also need the ability to compute the address of the target instruction. That ability is provided by the jump instruction, which simply sets the program counter to the value from register RA. Like branches, jump will write the PC plus 4 value into the specified destination register. This capability is very useful for implementing procedures in beta code. Suppose we have a procedure square root that computes the square root of its argument, which is passed in, say, R0. We don't show the code for square root on the right except for the last instruction, which is a jump. On the left, we see that the programmer wants to call the square root procedure from two different places in his program. Let's watch what happens. The first call to the square root procedure is implemented by the unconditional branch at location hex 100 in main memory. The branch target is the first instruction of the square root procedure, so our execution continues there. The BEQ also writes the address of the following instruction, hex 104, into its destination register R28. When we reach the end of the first procedure call, the jump instruction loads the value in R28, which is hex 104, into the PC, so execution continues with the instruction following the first BEQ. So we've managed to return from the procedure and continue execution where we left off in the main program. When we get to the second call to the square root procedure, the sequence of events is the same as before, except that this time R28 contains hex 67C, the address of the instruction following the second BEQ. So, the second time we reach the end of the square root procedure, the jump sets the PC to 67C, and execution resumes with the instruction following the second procedure call. Neat! The BEQs and jump have worked together to implement procedure call and return. We'll discuss the implementation of procedures in detail in an upcoming lecture. That wraps up the design of the beta instruction set architecture. In summary, the beta has 32 registers to hold values that can be used as operands for the ALU. All other values, along with the binary representation of the program itself, are stored in main memory. The beta supports 32-bit memory addresses and can access values in 2 to the 32nd or 4 gigabytes of main memory. All beta memory accesses refer to 32-bit words, so all addresses must be a multiple of 4 since there are 4 bytes per word. There are 2 instruction formats. The first specifies an opcode, 2 source registers, and a destination register. The second replaces the second source register with a 32-bit constant derived by sign extending a 16-bit constant stored in the instruction itself. There are 3 classes of instructions: ALU operations, load and store for accessing main memory, and branches and jumps that change the order of execution. And that's it! As we'll see in the next lecture, we'll be able to parlay this relatively simple repertoire of operations into a system that can execute any computation we can specify.